Okay, folks. Before we get rolling with this lesson, there's a little bit of a warm up here, and they just kind of want us to factor these best we can. So maybe we can just do them together. Oh, well, that's frozen. Perfect. Let's get rid of that. Okay. So this first one here, if you were to classify this trinomial as simple or complex, what would you call it? Oh, sorry. Yeah. Does anyone need anything? Pencil, eraser, calculator, espresso, coffee? Anything else? Anyone? Absolutely. Is this first one here a simple trinomial or is it a complex trinomial? And how might you know? Lauren? Why? Yeah, this a value here is equal to 1. It's 1x squared. So when we're dealing with this thing here, simple means that a value is just 1. And the way we factor these, now listen, you actually could use magic x for these ones. I know I told you, I'm like, okay, something times something equals 45, something plus something equals negative 14, and that's actually correct. You're right, that is exactly how we taught it. It's how we did it. We got really good at cracking the code. But now that we're experts, and I truly mean that, we're experts on this magic x and factoring complex trinomials, think about it like this. If we did the magic x here, the a value, like Lauren says here, is 1, and 1 times 45 is just 45, so we're looking to multiply to 45 and add to negative 14. And look at that, like, very, very similar. So check this out. What are the magic numbers here? Negative 9 and negative 5. And then using the magic x method, we were told to do what next? Presley? Yeah, we're going to divide each of these by the a value, which is 1. And we don't really have to reduce because it's over 1. And following that magic x method, what are the factors here? Yes, 1x or x minus 5 and x minus 9. And you would get the same way, you get the same answer if you did it any other way. So just so you know, when you're faced with a trinomial, magic x will work on all of them. If it's a trinomial, all of them. Okay, kind of nasty here, but kind of not. B, notice that each one of these terms, A, B, and C, are divisible by 3. So we're going to common factor out a 3. We got to keep that 3 out front of the brackets, and that's super, super important. And we get something like x squared minus 1x minus, well, okay. And again, you can magic x this or not. Multiplies to negative 12, adds to negative 1. I think those numbers might be, they got to be 1 away from each other. Yes, 3 and negative 4. I agree. We divide each of these by the a value, which is 1. Right? And when we write our answer, don't forget to keep that greatest common factor out front. We're going to have x plus 3 and x minus 4. Okay. Two x squared minus, ooh, nasty. Is this one simple or complex, and how do you know? Well, it's complex because we have a 2x squared. And yes, you know what? But also, Will, this one over here, it was 3x squared. But when we factored out the 3, it became simple, right? This is complex because, yes, it's a 2x squared. And also because we actually can't factor out the 2. So that's why it's complex. It's like, all right, we're going to have to deal with this 2 now. Question? Okay. Here we are. Multiplying to 24, adding to negative 11. What are those terms? 8, -8, -3, -8, -3. Okay, -8, -3. Divide each by the a value, which is 2. Reduce these. We get -4/1. And this one just kind of just stays -3/2. So we're looking at these guys on the ends. And there's no common factor, which is nice. So we got x minus 4 and 2x minus 3. This last one looks frightening, doesn't it? Can we common factor anything out of here? Oh, yeah, x and y. Yeah, that's right. So we're going to divide this by xy, divide this by xy, divide this by xy. Keep the xy out front of the bracket. And our new trinomial is y squared, yeah, plus 2y, okay, why are my y's different? And plus, anyone have any idea what's this going to end up being, Lauren? 1. That's right. Anything divided by itself is just 1. Close the bracket. Okay, good. Now, we're looking for two numbers that multiply to 1 and add to 2. 1 and 1. So we can say xy, y plus 1, y plus 1, right? But then we can also say, well, that's going to be y plus 1 squared. We can simplify it even more than that. Because y plus 1 times y plus 1 is y plus 1 squared. Cool? Questions about that? I know, got a little spicy near the end there. But I feel like that's where we're at. Okay, so I think at this point, I'm going to want you to put all your pencils down. I'm just going to need your eyes up here. This is not on your page. We're just going to talk about this. Folks, a square term. Square. You know why they call it a square? Well, really, a square term is the result of a term that is multiplied by itself. So when you say square term, think of an actual square, right? Every side length is the exact same size. So, for example, if this side length is going to be, I don't know, 3, right, then that means that they're all 3. And 3 multiplied by itself, like 3 times 3, equals 9. So that means that the 9 is the square term, because 9 is the result of a term, like the 3, that is multiplied by itself. Yeah? So maybe we can make a list of square terms. So far, we know that 9 is a square term. Does anyone have any other ideas about what a square term might be? Any other ones? What do you got, Ken? 25, that's right, because what number multiplied by itself gives you 25? 5 and 5, yeah, that's great, yeah. 16, and what number multiplied by itself gives you 16? 4, absolutely. 36, and that's 6 times 6, yeah. 49, that's 7 times 7, yeah, what else? 81, yeah, okay, great. 64, okay, we get the idea, yeah. Anyone got any other ones? Let's see how much we can go. Here, what do you got, Luke? What's that? Is it? Oh, okay. Oh, I know this one. That one. That one. What else you got? Oh, yeah, what? I'm getting carried away with these large numbers. Yeah, 4. Yes, of course. Yeah. Oh, yeah, 225. Is that 15? Okay. Oh, yeah, 100. Is it? What? Is it? Oh, okay, yeah. Okay, I like that. What's that? Is it? 625? Oh, okay, cool. 1. Yeah. 1. Yeah, 1 times 1 is 1. And like, oh, I love that you said that. That's actually so cool. 900? Is that, what's that? 300? 30? Oh, jeez, my brain. No, 900. Okay, that is awesome. Now, some people can just look at a number and just know that they're square because they just had so much experience, maybe in elementary school or maybe even in high school with square numbers. Remember you did the Pythagorean theorem? You're like 3, 4, 5, 5 squared. 5. So, yeah, big list of square terms. Now, question, can square terms involve variables? Okay, hear me out. Let's just say we have a square, okay, and we know a square term is the result of something multiplied by itself. So let's take, I don't know, 4x, yeah? And then that means each side here is 4x. And if we take 4x and multiply it by itself, we get, what do we get? 4x times 4x, Matt? 16x squared, and that's a weird thing because this is what we call multiplying monomials, and it's like you take the numbers 4 and 4, multiply them, 16, then you got to go to the variables. Now, when you're multiplying variables with the same base, yeah, or I guess terms with the same base, we add the exponents, right? Remember that? Now, that's one of those things in grade 9 that became a little bit weird, but we got it. Can we come up with maybe some more square terms that involve variables? Oh yeah, 9y squared. Yes, and that's the result of 3y times 3y. Yes? Let's got another one. Yeah, okay, 64d squared, yeah. 100f squared, okay. Now, we've fallen into this habit of, we see squared, and we're like, well, squared is actually squared. We know it's squared because that's what we say. We're like, oh, it's x squared. So we know squared is a square term. Now, think about this. Like what if the result of something multiplied by itself? Anything, can it be not squared? Can it be something else other than squared? Well, yeah, I think I do. You're talking square root, which I love. The square root of, so for example, let's look at my 16 over here. If we took the square root of this, we would actually get 4x, which were the numbers that we multiplied by itself. It's like the same idea when you take one of these ones and you square root 25, for example, and you get 5. And 5 was the number that we multiplied by itself to get 25. So square rooting is like going the other way. It's like the opposite of squaring. So that's so interesting. You know, I'm going to leave it at that, and I think that's enough. I think that's good. We have a good understanding of that. How about binomials? Can they be squared? Binomials? Like, can they be squared? Does anyone have an example of a binomial that is squared? Something multiplied by itself. We might have seen one on that first page. Do you see it? Do you see it? Y plus 1? Think about it. If we have a square, and this side length, well, they're all the same, but the side length is y plus 1. Y plus 1. Yeah? If we take y plus 1 and multiply it by itself, you know, y plus 1 times y plus 1, we just get y plus 1 squared. Yeah? And that's a square term. It is. Does anyone else know any other binomial squares? Well, let's throw 5x plus 3, and then that's it. Squared, yeah. As long as we got this thing here. It was very similar to your thought up here. You're like, oh yeah, oh baby, right? You see these squares, you're like, nice. Literally anything in brackets squared, we're good. It's a square term. You can have I don't know, negative 5x minus 300 squared, and it's a square term because it's a square term. We say it when we say it out loud. Okay. Are these terms square? Is 25 square? Is 10 square? 10 is not square. That's right. 144x squared. Square? 4x cubed. Not square. Like the 4 is square, but the x cubed is not square. 100y squared. Absolutely. And then 2x plus 3 squared. Yeah. Okay, that's squared as well. Now, the thing is, I don't know about you folks, but sometimes if I'm thinking, is this square or not? I think to myself, I'm like, okay, can I take the square root of 25? Oh, I can? Yes, I know it's square. Can I take the square root of 144? I can, it's 12. Can I take the square root of x squared? Yeah, it's just x. So yes, that's square. 4x cubed, like, yes, the 4 is square, but x cubed? No chance, that is not square. Okay. Here we are. What I would like you to do next is I want you to FOIL all of these. Expand and simplify. Really, we're talking about FOIL. Go ahead and FOIL these. Maybe not the last one. Maybe hold off on the last one wait for me on that one. But you FOIL it, I'll FOIL it, we'll all FOIL it. Okay. Whoop. And I always draw the arrows, and I highly suggest you do too. Whoop. Minus 4x, minus 6. Oh, that's good.
I didn't realize until I thought it was Jim. Oh, that makes sense. How comfortable. Yeah. Okay, so. Four squared
Plus 14x minus 14x minus 49. Okay. You guys getting that weird, like, two terms at the end? You know what I mean? Like, okay, sorry, are you getting 0x? Yeah? Yeah, weird. Okay, how about this? This one's got a 3 out front. This might change. 3x minus 15, x plus 5. And we FOIL this one, we get 3x squared plus 15x minus 15x minus 15 times 5. 10 times 5, 5 times 5, is this 75? It is. 75. Okay. Okay. Is that enough time? FOIL these? All right. Let's look at the first one. X minus 4, x plus 4. Okay, we FOIL it. And did you get x squared minus 16? Yeah, I did too. Strange that, like, eventually you get 0x there. I mean, did you need that middle line? Probably not, because you probably just saw, plus 4x minus 4x, and that was enough for you to say, oh, okay, x squared minus 16. Is that a coincidence or not? I don't know. Let's look at the next one. 2x minus 7, 2x plus 7. Hold on. X minus 4, x plus 4. Okay. 2x minus 7, 2x plus 7. And we do it again, do the whole song and dance, and again we get 0x. And we get 4x squared minus 49. Okay, the last one here, I thought it would change. We got 3, x minus 5, x plus 5. Do you see a pattern? What's going on with all three of the beginning factors? What's going on? The terms are the same. One bracket's adding, one bracket's subtracting, right? We got an x and an x. A 4 and a 4, one's minus, one's add. And that's happening for all of them. Look, 2x, 2x, 7, 7, one's minus, one's plus. X and x, 5 and 5, one's minus, one's plus. Question? Yeah, that b value is always ending up being 0. Yeah, it is. Look, 0x, right? 0x. That'll end up being 0x. And we're just left with this binomial, yeah, two terms. Now, let's look closely. Let's just at A and B. Notice the end result is x squared minus 16. Is x squared square? Yeah. Is 16 square? Yeah, absolutely. Now look at the factors. X minus 4, x plus 4. Interesting. It says here, there's a big spiel here. It says, notice that all the solutions in a binomial where the two terms are being subtracted. Yeah? This occurs when you multiply two identical binomials together, where one you are adding and the other one you're subtracting, two terms. And this is what we call, folks, a difference of squares. Difference meaning there's a subtraction symbol, right? Subtraction symbol. And squares meaning, okay, we got two square terms with a subtraction symbol. That's difference of squares. That's why they call it that. It's a very special case. And for these special cases, we have special ways to factor them. This one here is just for some theory. For sure, when we FOIL this, we're going to get m squared, right, plus mn, and then n times m is still mn, minus n squared. And, hold on, I think I goofed. Oh, this one's minus. Minus mn plus mn. And what happens is we always end up with this. You know what? No matter what the value of m or n is, you always end up with one positive, one negative, and which means it always ends up being nothing. So you end up with something that's squared, and a minus sign, and something else that's squared. You always end up in that sort of situation. What we're doing is expanding and simplifying, right? Going down this way. That's called expanding and simplifying. What we want to do here is we want to factor. We want to go this way. That's the way we want to go. So if you look closely, every single time we factor a difference of squares, one bracket's going to have a minus, and the other bracket's going to have a plus every single time. Look, minus plus, minus plus, minus plus, minus plus. They always end up being like that. So what we do is, if we wanted to factor, for example, this x squared minus 16, the way we factor it is we say, okay, we notice that it's a difference of squares because x squared is square and 16 is square, and there's a minus sign between them. So you got to think about it like this. Well, it's going to factor into something with a minus and something with a plus, for sure, because we know it's a difference of squares. From here, we think about the square root of x squared is x. Yeah? So it's going to be x minus something, x plus something. Then we take the square root of 16, which is 4. So we know that's going to be x minus 4, x plus 4. That's literally it. That's literally it. That's all we're doing. We're looking at the squares, difference of squares. Let's do an example. X squared minus 100. Does anyone have any suggestions or thoughts? How can we factor this? Way number one. Some people might look at it and think like this: x squared plus 0x minus 100, right? That might be what you're thinking, in which case, not the worst thing in the world, because something times something equals negative 100, or sorry, we're done with that, we're doing magic x. What multiplies to negative 100 and adds to 0? That's right, negative 10, positive 10. Lovely. Divide each by 1, the a value, and we get x minus 10, x plus 10. Sorry, that's a 10. That's one way to do it. However, there's a much simpler way. Think about the square root of x squared is x. The square root of 100 is 10. So what we're going to do is we're going to set up our brackets. We know one's going to be minus, one's going to be plus in no particular order. And we say, okay, x, okay, 10. And we're done. No magic x, nothing to think about. The hardest part here is maybe just identifying whether or not it's a difference of squares. In example B, this is where this method here kind of gets tossed out the window a little bit, because if you notice, 25x squared is certainly certainly a square term, yeah? 64 is definitely a square term. And look, they're separated by a subtraction symbol. So that's when an alarm should go off in our brain. It's like, oh, special case, here's a difference of squares. So we're going to take the square root of 25x squared, which is 5x. The square root of 64, not the square root of negative 64. Square root of 64 is 8. So when we set this up for an answer, we set up our brackets, right? One with a minus, one with a plus. And we have 5x. And the other one is 8. So it's 5x minus 8, 5x plus 8. And that is much quicker than trying to figure out 25 times 64. Woo! Take forever. How about the next one? Anyone have an answer, maybe? Maybe you're ahead of me. What do you got? Yeah, 2x minus 7, 2x plus 7. Yeah, I agree with that wholeheartedly, because I'm thinking to myself, yeah, this is a difference of squares. Square root of 4x squared is 2x. Square root of 49 is 7. 2x plus 7, 2x minus 7. Or the other way around. 2x minus 7, 2x plus 7. Now, it's all fun and games until you reach one like this. Because you look, you're like, oh, it's two terms. Yeah? 32, 50, okay, sure. Separated by subtraction, and that alarm's going off in your head for difference of squares. But is 32 or 50 a square term? They're not. So guess what? Are we doomed? What's the first rule of factoring? Who remembers? First rule of factoring. It's to find the greatest common factor. What's the greatest common factor here, do you think? I think it might be 2. So what we're going to maybe do here is I'm going to common factor out a 2 here, a 2 there, and we'll have 2 brackets, yeah? 32x squared divided by 2 is 16x squared. Oh yeah, you know where this is going? 50 divided by 2, 25. Whoa, okay, here we go. 2 brackets, oh, what are we doing here? We're going to have something in brackets. What does 16x squared minus 25, is that a difference of squares? See, we have to do a little bit of legwork here to make it a difference of squares. So we got 16x squared minus 25, and we're like, oh yeah, we know exactly what's going on. What does that factor into? Absolutely. 4x minus 5, 4x plus 5. The square root of 16x squared is 4x. The square root of 25 is 5. Throw them in brackets. Bing, bang, boom. What do you think? This is like that's tough. In this lesson, that's a tough one. Questions about anything? Okay, there's one more, and it's so gross that you need to see it though. Not sure if it'll ever come up, but you need to see it. Folks, we have two binomials here. We got 2x minus 4y squared, and we got 3x plus 7y squared. Is that up there a difference of squares? The rules for a difference of squares is that we have a square term minus and then a square term, right? This right here is difference. And these are the squares, like the square terms. Is 2x minus 4y squared a square term? Yes or no? Yeah, of course. Even if we go back, you told me anything in brackets with this square means it's square, right? And by that logic, 3x plus 7y squared must also be squared, right? So we're not going to do anything different. Might look a little bit different, but we're not going to do anything different. We're going to throw these in brackets, right? One with a, actually, I think I need more space. Throw these in brackets here. Just in case. One with a plus, one with a minus. And what we're going to do is put in, what's the square root of that? 2x minus 4y in brackets all squared. Well, think about it. A square root and square are like opposites. So we're just left with 2x minus 4y. That's the square root of 2x minus 4y in brackets squared. Because really what happened is the square root and the square are opposites. So it's going to be 2x minus 4y plus the square root of this one would be, I guess, just 3x plus 7y. Yeah? And then we would have the same thing in the other bracket. 2x minus 4y, 3x plus 7y. And I know it looks very weird. I completely agree with you in the idea that it looks very, very strange. But if you think about it, not much really changed. Take the square root of this number, bam, bam. Square root of this number, there and there. We did the same thing here. The only thing that's different is that the square root ended up being a binomial. And sometimes that can get a little bit messy. I'll show you what I mean. We're literally taking the red, this here, and adding it to this here. And when you add polynomials, it's not so bad. Now, in the second bracket, we're taking the red and we're subtracting it from here. And I know that when you subtract polynomials, it can get a little bit strange. So, let's work inside of these big brackets. So because we're adding two polynomials, what can happen is that we're allowed to drop all the brackets. Do you remember that? If you were in Mr. Todd or my class last year, when you had two polynomials beside one another and there was a plus, Mr. Todd and I would draw this happy face and be like, oh yeah, this is good. We love to add because adding says you can just drop the brackets, collect the like terms, and be done with it, remember? So just drop the brackets, minus 4y plus 3x plus 7y. In fact, I might even just finish off this bracket. I know I haven't touched that second one yet, but here's what's going on. You might remember this. 2x plus 3x is 5x, yeah? Negative 4y plus 7y is positive 3y. Do you remember that? Adding polynomials, it's been a while, I know. Now here's the thing about this second bracket. When we take these two polynomials and we're subtracting them from one another, Mr. Todd and I would do this. We would draw this guy. Who remembers that guy? Again, a couple nods. And we'd be like, oh. And the reason why well, us and him, the reason why we're all upset here a little bit is because what's going to happen is there's a plus out front of here, right? There's nothing out front of the first set of brackets. So we can drop them, no problem. But really, the minus out front of here, we have to now pretend there's an imaginary 1 and distribute a -1 to each term inside of there. Or really just change all of their signs. So instead of a positive 3x here, it's going to be minus 3x. And instead of a plus 7y, it's going to be minus 7y. And that is why that second bracket almost deserves its own attention, because it's a little bit weird. It combines a lot of prior knowledge. 2x minus 3x, -1x. And we have here -4y, -7y. We get -11y. Nasty, I know. Super nasty. Maybe you won't. Maybe you might see a few in the homework, but I couldn't imagine asking you something like that on a test. I don't think. It's a little bit rude. Unless the test were to be open book, and I'd be like, okay, maybe I'll think about it. But anyway, folks, that's all we got here. Page 230, 231, 3 to 7. I'm going to open up this book here and
No.